Okay, welcome to lecture 3 of module 3. Before we get started, I wanted to share this really cool project that some of your fellow students in the department are doing. So this is a project that is being done by EE84, which is a class hands-on ham radio taught by Mickey Lustig. And what they did was released a balloon from the top of Corey Hall. These are all EEC students. And this balloon was equipped with the following. What this is a solar cell right here, this horizontal thing. This is an antenna plus a GPS chip, as well as there's a small Arduino on it and a radio antenna, and these are 2 supercapacitors. So this was the entire payload of that balloon. And if you want to look a little bit more closely, this thing. No. Maybe this is a better way to do it. So this is the thing that's hanging off of it. This is the GPS antenna, the GPS chip. There's a little Arduino microcontroller here. So there's at least 3 things on here that should look vaguely familiar to 16A students. And what they did was they said, well, we're going to release this balloon from the top of Corey Hall. And we're going to actually use GPS to track where it's going. So what this shows is here it's being released in Berkeley. Then it crossed into Nevada, went over into Idaho, Wyoming, into Kansas, Missouri, Tennessee, South Carolina, and it has now left the continental United States. And how does this work, right? Basically, this antenna here receives the signals, exactly the same signatures that we've been talking about in class, from these 24 GPS satellites. And it figures out exactly what the propagation delay is. That's what this GPS chip does. This GPS chip then performs essentially the Trilateration Algorithm, which is what we're going to talk about today. Hopefully all of you figured it out between last lecture and now. And then the radio antenna basically transmits this to one of these several receiving stations over here. The protocol that they use is this protocol called Automatic Packet Reporting System, APRS. And once a particular tower receives it, they either rebroadcast or relay it or upload it to the internet. And that is how this map is exactly generated. So there's a balloon that was released from the top of Corey Hall 5 days ago. It is somewhere now over the Atlantic Ocean. We don't exactly know where, but it is being tracked, and it was made by students from this department using ideas that you are learning about in this class now. We haven't talked about every single detail about how to make this GPS chip, and we haven't talked about every single software implementation of the GPS algorithm. However, I'm hoping you can put all of these things together to see where you can go. So if you're interested in this kind of stuff, you can go ahead and take a series of classes, right? 120, 123, and then the ham radio class as well, to kind of build on these things. And as you can see, it's not really just one piece, like it's not one class that is being used to make this happen, right? There is stuff from multiple upper division level classes that are being put together to be able to realize this super cool project. So, when you're going through your career here, when you're, going through your classes, try to keep this hat on of interconnections between things and realizing that true engineering always requires you to synthesize different parts of things and different parts of the material and bring them together. So, remember to think about connections across classes. Don't necessarily say, oh, well, this is type A class, type B class, type C class. They all really come together, and you really need different types of techniques to make a complex system like this work. So I just thought that this was super cool, especially given that we are studying GPS now, and I wanted to show it off to you. So if you have any friends in this class, make sure to ask them for more details about how they actually made this. Okay, so with that, I will move to actually talking about the lecture. So we are module 3, lecture 3. And there's 2 announcements before we begin. First, you should have seen a Piazza post about the optional lab that is going to be happening. So this is a chance for you to try out a lab that we are considering offering in future iterations of 16A. But it is completely optional. There is, the only reason to do it is if you're really curious. And what this lab is talking about is it's talking about how to basically transmit an image using an audio signal. So there's details on the Piazza website. It'll talk also about ideas of correlation and encoding, decoding, wireless communication. So all of these ideas will be talked about in this lab. If you're interested, please check out the Piazza post and sign up. The second thing is that next week is going to be Thanksgiving week, so hopefully you will all get a nice break. We will have lecture on Tuesday, and so that there's no homework that will be due the Friday of Thanksgiving, that homework is going to be due on Monday, so you don't have to turn in the homework the Friday after Thanksgiving. Instead, you'll just be turning it on Monday. So make sure you look into this. These dates are all on the website and were announced, at the beginning of class, but just make sure that you're aware of this so that you don't forget to submit the homework. Okay. So what have we been doing over the past couple of lectures, right? We've been really thinking about how to make this GPS system work. And in the very first lecture, we focused on, which satellite is transmitting. And we used inner products to figure this out. The second lecture, we focused on, now I know which satellite is talking to me, but how do I figure out how far away that satellite is? So what was the distance and the propagation delay, right? And the technical tool that we talked about for this was correlation, which is essentially, as you've probably seen from discussion now, is just a sliding inner product, right? It's just inner product, but like one signal's moving along the other. And when the inner product, that shift at which the inner product is maximized is basically the shift that you're interested in. So this is just a moving inner product. So now that we have all of these distances of these different satellites from our position of interest, what remains to be done is how do we combine all of these signals to actually compute the location of our receiver, right? So how do we go from distances to location? And this is the Trilateration algorithm that we talked about briefly last time, right? And what did we see in this trilateration algorithm? What did we see when we set this up last time? This is where we ended in last class, right? What did you notice? What kind of equations did we get when we started trying to figure out, well, let's say I have one landmark here, or a beacon, or a satellite, or whatever you want to call it, another landmark, and I know distances from these 3 landmarks. Right? What kind of equation? How do I write that equation out? Well, if my position, let's say, is the unknown vector x, I have some origin here. I'm interested in my position. relative to the origin. And let's say I know that each of my landmarks are at positions vector A, vector B, and vector C. And I know my distances from each of these landmarks. What kind of equation do I get when I write out these distances? A quadratic, right? It's a second-degree equation. And, what do we do with second-degree equations? Have we developed some, months full of machinery to solve quadratic equations? Not in this class, right? There's definitely ways of solving quadratic equations and systems of quadratic equations. But here we're focusing entirely on linear equations. So the question is, how do we go from these quadratic equations to talking about a linear equation? And that's what we want to talk about next. And that is what the trilateration algorithm is. So now, what are exactly the equations that we have? Okay, I'll just move this here for now. So we have three equations, right? Let's say I have x minus a. This is equal to d1 squared. I have x minus b is equal to d2 squared. And x minus c is equal to d3 squared. Where do we go from here? We ended at this point in the last lecture, right? Any ideas on what we should be doing? When you see something complex and you're kind of trying to figure out what the next step to take is, what's a good standard way of progressing? Yeah? Try a simple example. That's an excellent idea. So we can try a simple example, and we kind of started with this 2D scenario, right? So we could go back to that, and I think that would be a perfectly great way of doing it. Today I'm not going to do a simpler example simply because we don't have enough time to do that in class. But on an exam, if you're in this situation, 100% I support doing that. Someone else had a hand? Okay. Another thing that you can do when you see some kind of expressions that are somewhat complicated is see if you can express them in simpler terms. That can also often help. So I want to just manipulate this equation. I have this equation 1, right? And I want to kind of pull out the quadraticness of this. So how can I write this norm in another way? I can write this as x minus a transpose times x minus a equal to d1 squared, right? And can I somehow rearrange terms to separate out the quadratic part and the linear part of this equation? So here, this is basically x transpose minus a transpose. And then I have x minus a. So when I expand this, what do I get? X transpose times x. I get basically the norm squared of x, right? When I multiply this out. What about a transpose times a? This gives me the norm squared of a. And then I have minus x transpose a minus a transpose x. This is equal to d1 squared, right? Okay. These two terms, are these two different terms here at the end? Not really, right? Because the order of an inner product doesn't actually matter. So I can just write this as x norm of x squared plus norm of a squared minus 2 inner product x a. Okay? So what is the annoying term here? The annoying term here is this quadratic term, right? I don't like this quadratic term. How can I get rid of this quadratic term? What I'm going to do is now I'm going to basically use a little trick. I can do this computation for the first equation. I can also similarly get the second equation in the following form. I can write it as norm of x squared plus norm of b squared minus 2 inner product between x and b is equal to these 2 squared. And the third equation gives me norm of x squared plus norm of c squared minus 2 inner product of x and c gives me d3 squared. So let's call this equation, let's call this equation 4, let's call this equation 5, and let's call this equation 6. So what happens now if I, let's say, take equation 4 minus equation 5? What do I get? 4 minus 5, what happens to these x squares? They cancel out. So I have norm of a squared minus norm of b squared minus 2 inner product xa plus 2 inner product xb is equal to d1 squared minus d2 squared. And now if I take 4 minus 6, can I write a similar equation? Why don't you just write it out to make sure that the algebra is correct? What's the most important property of the equation that we now have here? Is this now a quadratic equation anymore? We have used basically the fact that we had 3 equations to turn them into 2 linear equations. Right? Because these 2 terms are both linear in x. I can just rewrite this. So let's take this equation and rewrite it as this is basically minus 2x transpose times a, or let me actually write this as 2a transpose times x and plus 2b transpose times x equal to d1 squared minus d2 squared. Right? It doesn't matter which one I take the transpose of. I can write these in either order. So now you have a linear equation in x. How many variables are there in x, right? X is a degree, is a vector with 2 components. So I get 1 equation, I get 2 equations. So can I now solve for x? Right? So I've used basically the fact that I had these 3 beacons, I had 3 satellites. Even though they gave me quadratic equations, because of the form of the quadratic equations, I was basically able to manipulate them to becoming linear equations. Now, can you set up can you set up a matrix equation that basically you can use Gaussian elimination on for this? Right? That's just a question of algebra manipulation. Everyone with me here? Questions? Take a minute, think about it, talk to your neighbor, make sure from this point on you actually know how to solve this. Any questions? Is everyone with me? Oh, here. Thank you.
You mentioned that x is a knowing variable. I don't understand because you still have two squared variables and x was just a squared. So, like, what's the difference between a, b, and x?
So a and b, the question is, how many unknowns are there in x, right? X here is a 2D variable. So this is the x1 axis, x2 axis. So x is equal to x1, x2. So there are two scalars that are unknown. So if I have two scalar unknowns, I need two equations to solve them. Whereas I'm saying, what is my position relative to the campanile? And we're assuming that everyone knows where the campanile is. This is my position relative to Doe library, which is given by B, and we're assuming that everyone knows where Doe library is. So A, B, C are known. So when I have a norm of A squared here, it's just a number. Whereas the norm of x squared is x1 squared plus x2 squared. Does that answer the question?
Yeah.
Got it. Other questions? That's an excellent question. Everyone get that? Should it be minus norm of A squared? I don't think so, but you can check the algebra. It's just algebra. Other questions? Yes? Yes, it might be a minus sign error. That's exactly the question that he just asked. Other questions? Over there? No. Yeah, I didn't do this algebra right now. We can check. This might be a minus sign. Yes, this will be a minus sign. Plus. Okay. I don't really care about the algebraic manipulations. All I care about is that you see that this is a linear equation. And if you have two linear equations and two unknowns, then you can solve. That's the point. Question?
So since we're doing this right now in a 2D space, like if we do it in a 3D space, would we have to add like another satellite?
Excellent question. The question was, we did this in a 2D space and we had 3 satellites, right? So now we wanted to do this in 3D space, exactly. We would need to add a 4th satellite. Just like in a 1D space, we could do it with 2 landmarks, right? In a 2D space, we needed 3 landmarks. In a 3D space, we will need 4 landmarks. So, exactly. Yes, question? The question was, is the pattern because you're trying to get rid of the quadratic term? Essentially, yes. Because you can think about it in 2D when you have basically 2 quadratic equations, or 2 circles will intersect in 2 points. You need a way of disambiguating which of those points it is. Other questions? Okay, so we're all on the same page about trilateration? Everyone gets it? So this is the computation that is being performed by the GPS chip. Right? Except there's a little bit of a problem, right? What happens if, this is a small little chip. It's doing some computation. There's lots of other interference going around. What if there's some, noise in the system that makes it feel like your GPS or your satellite is at a slightly different distance than you thought it was? You get a reflected measurement of the GPS signal. You have some tiny little errors, right? What happens in the trilateration algorithm, let's say I have these 3 circles, but what if, actually maybe I can draw here, what if instead of getting 3 circles that intersect at a point, I get the following? Right? Where now is my location, right? I get these equations, but are these going to be consistent? Am I going to be able to solve them? Is there going to be a unique solution? No, right? We know that even when you have n equations and n unknowns, it's possible that you might not have a unique solution. So this is basically what we want to deal with in the rest of the class, which is we're going to get to part 4 of the problem, which is dealing with noise. And this is going to take us to the least squares algorithm and projections. And that's the technical tool we're going to use. So that's the agenda for the rest of our lecture today. Okay. So, which paper do you want? The equations or the summary? Summary. No? Okay. So, typically, we, have systems of equations. When you write a system of equations, we think of a system of equations as AX equal to B. Right? What we want to think about now is how to solve a system of linear equations when we don't have AX equal to B. We have AX is approximately, how do I spell approximate? M-A-T-E, approximately B. Right? What does this mean? This could be even just the imaging lab, right? You have all actually already experienced noisy measurements. When you're taking your measurements during the imaging lab, what you collect back using your photodiode, you can see that there's noise in there, right? Your image that you get out isn't perfect, and that's because, sometimes you collect light that comes in from somewhere else. It's not just the reflected light that you get slight reflections from other places, and there's all these kinds of issues that show up, right? And so you tried improving on it by thinking about the eigenvalues and designing a clever measurement matrix. But we're going to talk now about another technique that uses more measurements to actually get rid of this noise. And what we're going to think about is now, how do we solve these systems when AX is only approximately B? So what I want to do is I want to find an X such that AX is as close to B as possible. So when I look at my options in terms of these AXs, right? AX, what is the dimension of AX? AX is a vector, right? A is a matrix, X is a vector, but A times X is just a vector, right? Everyone remember that? B is a vector. So let's say I have some vector B in my space. This is my vector B. Okay? What are the possible values that AX can take? AX represents all of the vectors that are in the column space of A, right? AX always belongs to the column space of A. So if I want to think about and just draw a picture of this, or a cartoon picture, I can think of, well, maybe this is the column space of A. And This is my origin. This is 0. And I can choose any AX in this plane, right? If this was the column space. Any of these are valid values for AX. And I want to say, well, where can I go in the column space of A such that I'm closest to B? Right? Does everyone see what we're trying to do here? Yes, question.
So are you saying that B is not in the column space, so we need the best approximation?
Great question. Are we saying that B is not in the column space? And the answer is essentially yes. If B was in the column space, we could say that we can exactly solve this equation, right? But sometimes you will end up with noisy observations that will lead to B not being in this column space. If B was exactly in the column space, then A inverse B would give you exactly the solution you wanted. But now we want to start thinking about cases where A inverse B either doesn't give you the solution, or we cannot compute A inverse because A is not square. So this is what we're going to move towards. There was another question over here somewhere? Same one. Okay. So, we want to think about cases, the interesting cases here. A is not square. In fact, we want to think of A is an M by N matrix. And we want to think in particular about cases where we have more equations than unknowns. Why do we want to think about this case where we have more equations than unknowns, right? Because this is something, if, let's say, I know that my observations are noisy, right? What do I want to be able to do? I want to be able to just basically be able to take multiple measurements to somehow average away the effect of the noise, right? Like, for example, if we're looking at scores of students on 16A homework, right? We know that sometimes there's a little bit of noise that creeps into the system. You don't do as well, or you do as well as you potentially could have. So we take averages across all of the different scores to get a good sense, because there's noise in measurement. Because every single time you submit a homework, it's not exactly the same level of performance. Similarly, when you're taking measurements of any real system, if you have noise, what you want to do is you want to be able to take these multiple measurements to basically get rid of the impact of noise. And so that's what we're going to be thinking about here. So to be able to solve this problem and to be able to really understand how to go from here, I want to now come back to the suggestion that was made at the beginning and start with a very simple example. So, let us think about this very simple case where A is just essentially a vector, thank you, and B is also a vector. So A I'm thinking about as a 2 by 1 matrix. B is a 2 by 1 vector. Essentially here, A is also a vector. And I want to say, well, let me think about this A. Right? I can also call this just this A vector, because in this special simple case that we're thinking about the case where this matrix is essentially a vector. And I have some B. Do you see how this is basically a simple version of this? Right? Now we're allowed to move in the span of vector A, right? We're allowed to move anywhere that's basically some scalar multiple of the vector A. And we want to say, what is the point along this vector? And remember, we can take negative steps. That is closest to the tip of this vector B. That's what we want to find. So maybe from geometry that you've looked at before, do you have an intuition of what that's going to be? Yeah, at the back? Right triangle, right? Create a right triangle. What do we know? We have a theorem from geometry that says that the shortest distance between a point and a line is given by the perpendicular from the point to the line. Right? So what this is saying, well, from here, let's call this point P. From P, draw this perpendicular to the line. This point Q is the point along A that is closest to the point B, right? So now, since we've done this in geometry before, but we want to do this proof using, vector ideas, let's think about this vector here as being the vector z. So if I call this the origin O, this segment OQ is basically represented by the vector z. And we have this distance PQ, right? So what do we know about z? Z is basically, we know z must be some alpha times A, where alpha is a scalar, right? Because z belongs to the span of this vector A. How would you now use basically your intuition from geometry to try and show that, the closest point along A is actually just this point here, Q? We can say that, well, let's suppose, right? Let's consider, let's say hypothetically, there was some other point that was actually closer. Let's say that there was some point here, let's call this, let's say R, that R is actually closer to P than Q is. Then I can consider this triangle, PQR, right? Say R is closer to P than Q is. So what this is saying is that, well, PR is smaller somehow than PQ, right? The length of PR is smaller than PQ if R was closer. But as was pointed out, what do we have here? What does this make you think of? How do you want to proceed from here? Someone who hasn't spoken yet. Yeah. You could write out the Pythagorean theorem. Do you have to even write out the Pythagorean theorem? What does the Pythagorean theorem say? It says that the length of PQ square, Pythagoras says that PQ squared plus QR squared is equal to PR squared, right? So, what does that mean? This means that length of PR must be larger than the length of PQ, right? Because you take the length of PQ and you add something, which gives you PR. the hypotenuse, right? This is the hypotenuse of the right angle triangle, is always the longest side of a right angle triangle. So what this means is that whichever point it is that makes this right angle triangle is actually the closest point to the point P. Okay? So the hypotenuse is the longest side. And this says, therefore, this vector z is basically the closest point. If we wanted to represent this segment PQ using a vector notation, how could we write it? We could write it basically as this vector B minus this vector Z, right? Because Z plus this vector going here gives me B, right? This vector plus this vector gives me B, so this vector must be B minus Z. So I can write B minus Z is therefore smaller than B minus U. If, let's say, I called this other vector U, any other vector U. This Z is called the projection of B onto A. So a projection of one vector onto another vector is basically, if the projection of B onto A is that vector Z that is in the span of A, it's basically along this line, but it's as close as it can be to B, to this vector B, right, to this point P. And you can see that this basically makes sense. You don't want to go all the way far out over here. You don't want to go all the way far out over here. You're going to basically try and choose this point that is as close as possible. Yes, question? Oh, basically B minus Z squared is PQ squared. And B minus U squared is PR squared. Right? This is PR squared, and this is PQ squared. Right? Everyone with me here? Any questions? This is basically what you have just done, you have just done least squares for a simple system where, everything is two-dimensional. This is the least squares algorithm. All of this. That's it. Nothing more complicated. Yes? Yes, that is exactly what we're going to do next. Question? Should there be a square next? Yes, there should be a square here. Thank you. Other questions? At the back? No. Yes. Does A represent our column space in this problem? Yes. In this case, because the matrix A is just a column vector, the column space of that matrix is the span of that vector. So the span of A represents the column space. Yep, great question. Yes, question. How do I know the column space is a plane? We haven't gotten there yet, right? So, in general, the column space will not just be a plane, it'll be a hyperplane. But we can't draw those. So I drew a plane. Good questions. Any other questions? Also, the word hyperplane Plane is something that is two-dimensional. Hyperplane is just the generalization of that concept to higher dimensions. Except we don't know how to draw or visualize these things, so we don't. How would we get the value of alpha? Thank you. I was going to ask that question, but you asked it for me instead. So let's get the value of alpha. Right? We have this z, and we've computed it by basically, we said, well, you can draw this perpendicular. But a computer who wants to, let's say, solve this system or compute this projection cannot really draw a picture and then draw an angle and then measure, right? That doesn't work. How can you algebraically compute the value of this alpha? So let's do that next. How do we find alpha? So why don't you take a minute to think about it? Like, discuss with your neighbors, spend some time. Basically, I'll give you a big hint. We just discussed something in the last few lectures that connects vectors to the angle between vectors. And here we care about the angles between vectors. So maybe that'll be helpful. So take a minute to think. Question or an answer? Okay, then hold on. So how many people think they have an idea for how maybe you can kind of proceed? Okay, a few people. How many people want another minute to think? Everyone wants to kind of proceed together? Okay, let's do that. So yeah, there was a suggestion at the back. Yeah, do you have a suggestion? Wouldn't alpha be b plus z? Oh, this is not focused. So yeah, good question. So let me just draw this out again. So we have this vector z here. We have this vector b here. And this b should go a little bit higher. This is b. Okay? These are the two vectors we have. And we have this third vector here. And let me call this vector y. Right? So I have now vector z plus vector y equal to vector b. B is equal to z plus y. And so if I wanted to write y in terms of b and z, I could write y is equal to b minus z. Right? So that's just the name of, you can think of this vector. That's where this b minus z came from. Right? I'm just basically saying that I can write this vector as b minus z. Okay? But what we want to find out, we know that z is equal to some alpha times a, and the question is, how do we find this alpha? Other person, yeah. You, exactly you. Yeah, suggestion, yeah. Mm-hmm. Mm-hmm. So there's this suggestion that's saying, let's look at inner products, right? The suggestion is saying, what is the one technique that we have that connects vectors to angles? And that's inner products. And we can look at basically the inner product between this vector B and the vector A, right? And if we have some theta here, that inner product will tell us something about the angle between vector B and vector A. So it's possible to try and compute going forward from that, but there is actually an even simpler way. And part of this comes from the fact that what is the case where the inner product becomes 0? When things are perpendicular, right? And zeros are so much easier to deal with than any other numbers. So can we write an equation that concerns angles in these vectors but equates to 0? So I know that this is vector A over here, right? What is the angle between this vector A and this vector Y? 90 degrees. So if I take the inner product between this vector A, building on the idea that was just suggested, between this vector A and this vector Y, what do I want to get? 0. So if I write A inner product Y, this is equal to 0. But this is just A inner product of B minus Z equal to 0, right? I can further write this as now A transpose B minus Z equal to 0. But what is Z? Z is just alpha times A. What do we want to find out? Alpha, right? So let's substitute that in. So now I have A transpose B minus A transpose times alpha times A equal to 0. So I know A, I know B, I know A transpose, I know A. So the only unknown here is now alpha. So I can write basically this gives me, I can write this as the inner product of A and B minus alpha times the norm squared of A equal to 0. Therefore, alpha is equal to inner product of A, B divided by the norm squared of A. Here's the formula. Here's the least squares algorithm. This answers the question that was just asked, which is, well, how do you compute this value of alpha? And what we did was we used the fact that we had just learned something about inner products that tells us, that connects basically geometry to algebra, right? It used the geometry that says that, okay, these must be orthogonal, these must be perpendicular, to then allow us to actually compute the value of that vector. In discussion, you're going to see actually two alternate ways of proving exactly this idea about projections, or this least squares algorithm, in the simple two-dimensional case. We've done one way of proving it, we've done one derivation. You're going to see two different ways because it's just such a fundamental idea that we want to make sure that you see as many different ways of thinking about it as you possibly can. So, let's think about this a little bit, right? Let's play with this a little bit more. What if I told you that I want you to project A, or let's say project B onto A, and B is already at 90 degrees. you have the following situation. This is your A, this is your B, and you want to project B onto A. What is the projection of B onto A? 0, right? Because this inner product is going to give you exactly a 0. What if instead the B vector was like this? If this was the B vector, it was aligned with A but in the opposite direction. What would you get? You would get basically, what if B was equal to minus A? You would get alpha equal to A minus A over norm A squared. But this just would be minus norm A squared over norm A squared, which is equal to minus 1. Right? What if B was equal to A? Project something along itself, well, you just get the vector, right? So intuitively, you can see that these cases where we intuitively know the answer, things match up perfectly, right? Now we can really come and build to basically not just this 2D case, but build out to the general case, right? What happens when A is not just a column vector, but the columns of A actually have a column space that is, arbitrary? That's really the general case that we want to start thinking about, right? Always we've done in that case, we've said, well, let's take the inverse of A. But we've always assumed that B belongs to the column space of A, right? The question is, well, what if we can't do this? What if that solution doesn't work? So, now, moving beyond 2D. Projections generalize. So, before we really just, build this out, I want to explore now orthogonality in the context of not just two-dimensional systems, but more general cases. So, orthogonality beyond 2D, right? Because as we can see, these 90-degree angles and these projections are playing really important roles in finding these best fit, or these best solutions, even in the presence of noise. So for this, I want to propose the following theorem that I want to think about. We're going to do this, and then we're going to connect back to the more general case. So now consider a matrix A, and let Y belong to the column space of A. Okay? Let A be A1, A2, AN. So these are the columns of A. A1, A2, AN. Okay? Let Z be a vector such that Z is orthogonal to A1, Z is orthogonal to A2, and Z is orthogonal to AN. Okay? So, I have the columns of A, and I have a vector that is orthogonal to every single one of those columns. Okay? Then, what is the relationship between Z and Y? If Z is orthogonal to every single one of the columns of A, what happens to Z and Y? Let's draw a picture, right? Again, I'm drawing a plane because that's the only thing I can draw, but let's say this plane represented the column space of A, right? Or actually, let's do it even better. Let's say the table represented the column space of A, right? And I have all these vectors that are lying in this column space. and I have this vector z. It's pointing like this, and it's orthogonal to this vector in the column space, it's orthogonal to this vector in the column space, it's orthogonal to all of these vectors that make up the columns of A. If it's orthogonal to all of the columns, it must be actually orthogonal to every single vector in the column space, right? Because this angle is going to be 90, like this vector is always going to make a 90-degree angle with any vector in the plane. That's what we want to prove. So we want to say then we have that the inner product between z and y is also 0. So z must be orthogonal to any y in the column space, if z is orthogonal to all of the columns of A. Does everyone understand what we're trying to show? Why do we want to show this? We want to show this because then it allows us to focus just on the columns of A when we want to say something more generally about the column space. Okay? So, how can we go about doing this? So how do we prove this theorem? Why don't you take a minute to think about it on your own? In the meanwhile, are there any questions? Yes. Great question. We're given that y belongs to the column space of A. We're given that A is made of these columns. We're given that z is a vector such that it is orthogonal to each of the columns. And we're trying to prove what comes after the then, which is that z times y is equal to 0, or inner product of z and y is 0. Okay, so how do we go about proving this? Any suggestions? Someone who hasn't spoken yet. Yes?
Well, we know that y must be a linear combination of the columns of A between the columns.
Great suggestion, right? We know that y belongs to the column space of A. So y is a linear combination of A1 all the way up to AN. So I can write y as, let's say, some C1 times A1 plus C2 times A2 plus Cn times AN, right? Okay, I know that y belongs to the column space. Now, what do I want to do? I want to explore this quantity, this inner product of z and y. I can write this as the inner product of z, and I can just substitute what I know about y, C1a1 plus Cn/an. But what do I know about inner products, right? Inner products are linear, so I can separate this out. So I can think about this as z inner product with the first term, z inner product with the second term, z inner product with the last term. So this is z C1a1 plus z inner product C2a2 plus z inner product Cn/an. Does the constant matter here? Right? This is basically just this constant comes out, z inner product A1 plus z inner product AN, Cn. There's no C. But what are each of these terms? 0, right? QED. It was that easy. Okay, but I didn't do it. I just followed the suggestion that came from you folks. So, good job. Okay, so what have we shown here? We have shown, therefore, that if this z is perpendicular to the columns of A, that it must be perpendicular to all of the vectors in the column space. Okay? Everyone with me here? Any questions about this? Okay, because this is important. Like, this will build. Okay. Good. So now, let's go back to our least squares problem. I have now AX is kind of like B, right? These squiggly equal to's means approximately equal to. And let's say A is now an M by N matrix. So there's M equations and N unknowns. And there are more equations than there are unknowns. Furthermore, we know that these are noisy equations, right? We know that when we're taking measurements in our imaging lab that maybe some external light crept in. We know that when our satellite is transmitting, maybe there was a slight, issue with the transmission, or there was some interference that made us made us miscalculate the propagation delays. Something happened, there's some little bit of noise somewhere, right? So these equations aren't perfect. What is our goal? Our goal is to find X such that AX is close to B, which in particular, if we think of this as an error vector, we can think about, we want to minimize the length of an error vector, where we define this error vector as AX minus B. Right? In our 2D case, this PQ was our error vector, right? Z was basically our AX. This was B. So the length of PQ was the length of our error vector. Everyone see that? This is important. Everyone see how this PQ is the same thing here? Okay, good. And let's think of A again as these columns, A1 all the way up to AN. Now I'll go back to my picture here. Everyone see this picture? So now let this plane represent the column space of A, and let this B be the vector that we're trying to match, right? What do we now want, right? If we want to find a point in this plane that is closest to B, which point do I want to find? What do we want to do? We did it in the two-dimensional case. What do you want to do here? I have a plane. I have a vector. You want to find the projection, right? You want to find, basically, where does the perpendicular from B hit my plane, right? We can make sense of this in 2D. We can make sense of this in 3D. In 4D, we cannot visualize it, right? But how can we write it algebraically? What does it mean for something to be perpendicular to an entire subspace or vector space or column space? Well, we just proved a theorem about this, right? So we basically want to find the orthogonal projection of B onto the column space of A. So, I want to now find that Z in the column space. This is the column space of A. So this is Z. This is B minus Z. I want to find that Z such that B minus Z is orthogonal to the column space, right? So I want B minus Z. Let us call this Z. I want B minus Z times this inner product with A1 to be equal to 0. I also want B minus Z inner product with A2 to be equal to 0. And I want B minus Z inner product with AN to be equal to 0. Right? Because what we just said was that in order to be orthogonal to an entire column space, I want to make sure that my vector of interest is orthogonal to every single one of the columns. Is everyone following me here? Any questions? Yes? So I'm just saying that this A times X, so here we had, last time we were thinking about, remember, Z was alpha times A, right? So now we're going to say A times X is equal to some Z. Right? So Z, this is AX equal to Z. I want to find X. So X in this multidimensional case is the same as the alpha in the two-dimensional case. So the error now is basically the difference between Z and B, which is the length of this vector. But that's given exactly by this. Yeah? Good question. Yes, question.
So does the order not matter, like AX minus B?
Great question. It doesn't matter whether we write AX minus B or BX minus A. It doesn't, because all we care about is the length of that vector. The orientation of the vector would care, but because we're only minimizing the magnitude, the order doesn't matter. Good question. Other questions? Okay. So, we now know what it means to be orthogonal to the column space, and we just wrote out the conditions for that orthogonality to that column space, right? So I can now write these out a little bit more explicitly. I can say A1 transpose times B minus Z is equal to 0, all the way up to AN transpose times B minus Z is equal to 0. Right? What I want to do, so what are these A's? These are now A1 transpose, A2 transpose, these are row vectors, right? So I can write A transpose is equal to this row A1 transpose all the way up to AN transpose. Right? This is just the transposed version of A. All of the column vectors became row vectors. I want to take this and write it as a stacked set of equations. So I'm going to stack all of these. I'm going to write this as A transpose times B minus Z is equal to 0. Right? This is a row vector times a column vector. This is a row vector times a column vector. So these equations are of this shape. This is a row vector times a column vector, right? This is a row vector times a column vector. But the column vectors are the same in every case. So what I'm doing is I'm just stacking up all of these rows to get me this A transpose here. Does everyone see that? Okay, good. I'm going to manipulate this further. This is very similar to the calculation that we did in the 2D case. Z is now AX. This is equal to 0. I can build this out further. A transpose B minus A transpose times A times X is equal to 0. What do I want to find? I want to now write this. I want to be able to write this in a way to figure out what my X is. So I can write now A transpose AX is equal to A transpose B. Now, what is the dimensions of A transpose A? A, remember, is an m by n matrix. What are the dimensions of A transpose A? N by n, right? Is this a square matrix? Can I invert this? So I can write X as A transpose A inverse A transpose B. This is the general least squares algorithm. This is also called a projection of B onto the column space of A. There's a question, of course, to be asked here. Is A transpose A always invertible? Are square matrices always invertible? No, right? So this is something we have to worry about, but we're not going to worry about it today. We're going to worry about it in the next lecture. But what I want you to see here is basically how what you did in the general case is exactly what you did in the two-dimensional case. You have now derived the full least squares algorithm. You know how to deal with noise in the case of GPS systems. We'll pick up on Thursday.